Sound waves. The nature of sound wave. First, sound waves needs a medium for its propagation. The medium may be gas, liquid, or solid. How to prove it? First, put a belt inside a gas jar. Then, when the hammer of the belt hits the metal part, sound is produced. Then we use a vacuum pump to remove the air inside the jar. During this motion, the intensity of the sound wave drops to zero, even the hammer still works. This proves that air is the medium for sound to propagate. The next nature is sound wave is an example of longitudinal wave. How to prove it? First, put a candle near a loudspeaker. Light up the candle. Then connect the loudspeakers to a signal generator. And switch on the signal generator and set the signal generator to a frequency of about 50 Hz. When sound wave is produced, we see that the frame is observed to vibrate to and fro. This shows that the air molecules of the sound waves vibrate in a direction parallel to the direction of wave propagations, which shows that the wave is longitudinal wave. Notice that for a longitudinal wave, there are compressions and rarefactions CR and the separations between successive compressions or successive rarefactions is the wavelength of the wave. The compressions and rarefactions are propagating in the directions parallel to the direction of the wave travel. However, the particles are only vibrating. They are not propagating in the directions with the wave travel. The third nature of sound wave is that the speed of sound wave V depends both on the density of the medium and on the temperature. In fact, the higher the density, the greater the speed of the sound. Since density of solid is greater than density of liquid, which is greater than the density of gas, therefore, speed of sound in solid is greater than the speed of sound in liquid, which is greater than the speed of sound in gas. The typical order for speed of sound in solid is about 3,000 meters per second, and the speed of sound in liquid is about 1,000 meters per second, and the speed of sound in gas is about 330 meters per second. To demonstrate sound can propagate in solid, we can connect two paper baskets with a piece of string, and when one speaks in one basket, the sound wave can travel along the string towards another person on the other side. Speed of sound wave also depends on temperature. Generally, the higher the temperature, the greater is the speed of sound. Number 4. The loudness of the sound wave is described by using sound intensity level. The symbol is L. Number 5, there are musical notes, 音符. This is a symbol for a tuning fork. 音叉. A tuning fork produces a pure note with the waveform like a sine wave. For a tuning fork, the pitch 音調 is related to the frequency of the sound wave, and the loudness is related by the amplitude of the wave. That is, pitch is related to frequency F, loudness is related to amplitude A. Take for an example, this is the original musical note. If we increase the loudness of the note, then the wave will have greater amplitude. If we decrease the loudness of the musical note, then the amplitude of the wave will decrease. If we increase the pitch of the sound wave, then we have a greater frequency. However, if we decrease the pitch of the musical note, then the frequency of the wave will decrease. Notice that musical notes of the same pitch played by different musical instruments have different qualities, 音質, because they have same frequency but of different waveform. Consider the case of a note played of frequency played by a piano and the same note of frequency F played by another instrument, for example violin. From the graph, we see that both notes have the same frequency, but the waveforms are different. Therefore, these notes have different quality since they have different waveform, even though the frequency are the same. Number 4, when the string of a musical instrument is plucked at the middle, sound wave is produced. What are the similarities and difference between the wave traveling along the string and the sound wave produced by the vibrating string? For the wave along the string and the sound wave produced by the string, they have one thing equal, which is the frequency. However, the wave traveling along the string is transverse, while the sound wave produced by the string is longitudinal. Also, the wave along the string is stationary, and the sound wave produced by the string is traveling. And the wave speed along the string is given by the equations v equal to square root t over mu. T T is the tension of the string, mu is the mass per unit length of the string. However, the speed of the sound in air is about 330 meters per second. So, therefore, their speeds are not equal. Since the speeds are not equal and the frequency are the same, therefore, the wavelength of the wave along the string, lambda, and the wavelength of the sound in air are not equal.